So for an amine, we have R group NH2, and then it's an amide or amide. Now, similarities between the two are that, of course, they both contain nitrogen, and nitrogen is in group 5, so it's going to contain 5 valence electrons. Let's just quickly draw the Lewis dot structure. 1, 2, 3, 4, 5. So nitrogen likes to make 3 bonds, and of course the extra 2 electrons are a lone pair. So let's just punch the lone pair in here and over here. That's going to give these compounds, or at least the amine, very unique properties, because amines are basic, albeit weak bases. So why are they basic? Well, the first thing we have to do is let's just draw a typical amine here. I could draw a tertiary amine and say the N is surrounded by 3 ethyl groups. So if nitrogen is attached to 3 carbon-containing groups, that means that this is a tertiary amine. And we can just abbreviate that here. What I drew up here, this R group is some carbon-containing group. This would be considered a primary amine since the nitrogen is only attached to 1 carbon-containing group. And the secondary amine would be if nitrogen was attached to 2 carbon-containing groups. So this is your tertiary amine, again, because it's attached to 3 carbon-containing groups. I'm going to draw in my, let's keep the same color here. I'll draw in my lone pair. And typical reaction will be to add this to an acid. HCl, hydrochloric acid. Let's select a pretty common acid. By definition, acids are proton donors. And by definition, if something is a base, it's a proton acceptor. Should say acid and base. A little sloppy there. So what will happen to an acid and water? Well, acid is going to do what it always does. It's going to dissociate. In water, especially a strong acid like hydrochloric acid, dissociates completely to give away its proton. And let's just review for 1 minute. If I have a strong acid, it's going to want to give away its proton. Why does it give away its proton? Well, because what happens is the electron that's left behind from the hydrogen to form the proton is happy, it's content, it's in a very stable place because chlorine wants to gain an electron. So since chlorine is a group 7 halogen, any group 7 halogen hooked up with hydrogen, as in this case, make pretty good acids, because they're always going to want to donate a proton. If you by donating a proton, you're leaving 1 electron behind, and this electron is pretty comfy here because all group 7s want to gain 1 electron to get an octet. So since the octet rule is fulfilled here, this forms what's called a stable conjugate base. If upon donating a proton, this acid here forms a stable conjugate base, then you know you have a pretty strong acid. So all acids want to donate protons, but the ones that form the most stable conjugate bases are the strongest acids. So that's why halogens make some, or compounds containing halogens make pretty good acids, like HBr or HI and so on. So form a stable conjugate base, you've now donated your proton. Quick side note, electron-rich parts of molecules will always want to go towards electron poor. Pretty much every reaction works this way. So you can build a little cheat sheet here. By electron-rich I mean something with a negative charge, something with a slightly negative charge, something with a double bond. Single bonds are usually not too reactive unless you combust them, but these two electrons here on the double bond can be broken a lot more easily. And you have in another, your fourth electron-rich possibility, there should be a dot, which is your lone pair. So electron-rich areas always move to electron-poor. The two types of electron-poor areas are a positive charge and a slightly positive charge. Small Greek letter D meaning delta for small change. So this needs to be written for every single reaction imaginable, and it may give you some idea of how the reaction is going to go. This way you have to memorize your reactions, but it'll be easier to recall if you understand where the electrons are going. And that's really all chemistry is. It's just movement of the outermost electrons from one place to another. So if I have an electron-rich lone pair here, well, what's going to happen? Well, you're going to follow the opposites attract rule. In other words, electron-rich areas will always move towards electron-poor. Minuses always go to pluses. Always, always, always. So this lone pair, since it's electron-rich, it's going to grab the proton, be attracted to the plus, electron-poor area. And what happens is this lone pair kind of flips up, almost like a almost if you were looking above like a swing door, a door that swings that's on a hinge almost, just kind of flips up like that, grabs the proton. So now what you have is that lone pair forming a single bond. And I'm just going to redraw what I have. We didn't do anything with the three ethyl groups. And since that lone pair formed a single bond, I'll draw those two electrons the same color. They now form this bond here. Two electrons make up every single bond. So now this lone pair is in the form of a single bond. It's now attached to the H. Okay. And again, one of these electrons is still attached to the nitrogen here. The other one kind of flipped up, almost like a door on a hinge or something, and it filled in the place of this plus here. So now you have a nice single bond. These two electrons form that single bond. Maybe I'll just draw them in here, but you don't really need to do that. If you draw that line, that's fine. Okay, but just to demonstrate, I drew just for more basic understanding, I just drew the two electrons in, but you don't need to do that. One single line is fine. So now that the electrons appear, this electron here was attached to the nitrogen, but now it's up here. So one electron left the nitrogen. This one's still attached to the nitrogen. So you need to put a positive charge on the nitrogen. It moved. So just place the plus anywhere near the nitrogen. If you leave it up here, it's wrong. If you leave it on the H, that's wrong. And if you look at your reaction, there are something else floating around. Your Cl minus is still floating around somewhere. And if you remember your opposites attract rule, electron rich will always move to electron poor. Well, you know that this counter ion, this Cl minus or this stable conjugate base, will be attracted to the plus. So what you do is you draw the Cl minus anywhere near the plus. Anywhere near the plus is fine. Because what's happening is it's not really forming a covalent bond where there's a sharing of electrons. Whenever you have a base plus an acid, this is going to form a salt. Salts are ionic or contain an ionic bond, so there's really no sharing of electrons anymore. So much stronger what's called electrostatic attraction. That's why I didn't draw a line from this N plus to this Cl minus. I mean, most of the times when you see an ionic bond being formed, they'll just put the charges where you have an electron here, you have a plus charge here, and they're very strongly bound to each other because of that electrostatic attraction. Since there's no sharing, covalent sharing of electrons, I can't draw that line there. That's the difference between an ionic bond and a weaker polar covalent bond or non-polar covalent bond. So salts are ionic, and that's really what makes salts have very high, also high melting points at room temperature, because again, that strong electrostatic attraction. So whenever you have a base plus an acid, you're going to get a salt. And this is a typical reaction of an amine with a strong acid. Now, it's worth mentioning that this particular amine is called triethylamine. And triethylamine is unique in the sense that it is a tertiary amine and has 3 ethyl groups attached to the end. And what you'll notice, especially if you work with this compound in the lab, that has a very strong odor. And that's because alkyl groups are electron pushing. Alkyl groups are electron pushing. So what that means is that there's an electron density surrounding these carbon-carbon bonds, these alkyl groups or these carbon-containing groups, these carbon chains, and that electron density is going to be pushing on the nitrogen, in turn pushing on the lone pair, making it more active. So since this lone pair is a little bit more active, or the electron pushing groups give a little bit more oomph, then you're going to get something that may be a little bit more of a stronger base, willing to abstract that proton. Okay, so it makes the lone pair a little bit more active since these are electron pushing. And since these are 2 electrons, these in turn are going to be a little bit more propelled a little bit more towards the plus. It's also why this particular compound really stinks, because this lone pair is pretty active. It's going to react a little bit more with the olfactory cells in your nose. So this compound you're going to want to be pretty careful with. This is a pretty potent base, albeit a weak base when compared to other bases. However, in relation to other amines that don't have these electron pushing groups, it's going to be this lone pair is going to be a little bit more active. So again, you want to be careful. These types of tertiary amine compounds, they really want to extract protons. So those are amines. Have bases. Amines are weak bases. They want to grab protons or accept protons. They like to react with strong acids such as hydrochloric acid. We know that acids are proton donors. Okay. Base are proton acceptors. We know that hydrochloric acid will donate a proton because strong acids always form stable conjugate bases. That's how we get that Cl minus on there. And of course, the lone pair will always want to move towards the H plus because opposites attract. Electron rich, one of these 4 guys here, will always move to your electron poor area. Always, always, always. Whenever you have a base plus an acid, you're going to get a salt. Salt contains an ionic bond. So it just so happens that if you were doing this reaction in lab, you may notice that, well, since this compound has some nonpolar groups on it, it may not be too soluble in water, maybe only slightly soluble, since water is a polar solvent, and these are nonpolar groups surrounding the nitrogen. Well, once you form that ionic bond, what you'll find is that it will go into water. It will most likely go into water a little bit more, because what an ionic bond is, it's kind of like a super duper polar bond. So what that means is that when you form this ionic bond, you form this compound into a salt, so the chloride salt of the original amine. It's going to be more soluble in water, because salts love water. They love to dissolve in water. Because, don't forget from your Gen Chem, your like dissolves like. These are rules that you'll find, pop up again and again in chemistry. So you got your like dissolves like rule, and then once you're talking about those polar characteristics of compounds, or compounds that have a little bit of a charge on it, or electron-rich areas, they're always going to want to move to electron-poor areas. So if we have an amide, let's just take a typical compound like acetamide. 2 carbon containing, that's a 2 carbon containing amide. Amides are a little bit different than amines. They contain this carbonyl group here. And we know that carbonyls have an electron-rich and electron-poor area. So this oxygen's electronegative. It's going to pull the electron density a little bit towards itself of this double bond. It's going to be electron poor. It's a plus. So this is an electronegative atom. Oxygen's in the top right corner of the periodic table. It's going to pull the electron density of this double bond a little bit closer towards itself, leaving this carbon a little bit electron poor. So it's going to be a delta plus. And all carbonyls have that. Let's isolate the carbonyl here. All carbonyls have that. It's a carbonyl group. All carbonyls have that characteristic. Yeah, in some of the other videos you may see me mention that. Okay. So all carbonyls have a delta minus delta plus. So what I also like to do is just to see what's going on, draw in your delta minuses and your delta pluses throughout your molecule. And I know that nitrogen is in group 5, so it likes to make 3 bonds. The other 2 electrons are part of a lone pair. And this looks very similar to our amine. So we would think that this lone pair here is basic. We know bases abstract or accept protons. So I had something like HCl again. We know that acid will dissociate in water, forming the H+, a stable conjugate base. And we know that the electron-rich lone pair will move towards, theoretically, should move towards the H+. But with amides that doesn't happen, or at least not to the extent as amines. Let's see if we can figure out why. Well, we know electron-rich always moves to electron-poor. But what happens when you have the addition of a carbonyl group right next door? There's some competition for that lone pair. This lone pair has a plus right here that it can be attracted to. So what will happen is it's going to become deactivated. This lone pair is not going to want to do this anymore. It's not going to want to abstract a proton because with this carbonyl group right here, it's getting this lever right at home. It found its opposite. It's found its opposite right here. So since this lone pair is now attracted to the carbonyl carbon, it no longer needs to abstract a proton from another molecule. So acetamide is super weak or not basic at all. So essentially that's why amines are basic and amides are not.